All right. So chapter one deals with units and unit conversions, precision and accuracy, and significant figures. In this course, we will deal with the SI system of units um, throughout the remainder of the chapters 2 through 10, as our status quo operation. But there are other systems of units that can be used in the real world. Your textbook covers some of those. But the main skill we want to develop from chapter one that will be with us through the semester is unit conversion. So let's say I have a unit of one type. Let's say we measure something in slugs. So one system of measures calls a unit of that measure a slug, and the other one calls it a snail. Well, they're measuring the same thing, but they may be called different amounts of that thing. So, for example, one slug might be equal to three snails, right? So then let's say I know I have five slugs. A skill that you want to be able to develop is how do I express the number of slugs I have in terms of snails? And it's always the same way. What you do is you set up conversion factors. A conversion factor is just something expressed two different ways that represents the same thing. So in this case, it would be three snails is equal to one slug. Well, now conceptually, I've placed something in the numerator and the denominator that are both representing the same thing, meaning this is a version of the number one. So I haven't actually changed anything, but I've set it up in such a way that the unit I had will cancel, and I'll be left with the different unit that perhaps I wanted to use. In this case, it would be 15 snails. And that's called unit conversion. And there's a number of examples of that in your PAL assignments and your reading. The second thing is precision and accuracy. And the example I like to use just to conceptually demonstrate what we're talking about, because a lot of people don't have a good intuitive understanding of what the difference in these two words is I like to use dartboards. We can have four examples. So in this case, you're kind of throwing the darts. You are the measurement system, and you could be wanting to hit. What a day. All right. So dartboards, precision and accuracy. So let's say this is a dartboard and you're aiming for the bullseye. So we're going to make four versions. Same nominal dartboard. I'm not the best at drawing here. And then you take three throws at each one. And let's see, we'll start, let's say this one down here will be accuracy. This will be precision. We'll start with the easy ones. What's easy, right? Um, you could make one, two, three. That's your first attempt over there. And you could have something like this. That's your next attempt. And then over here, you could have something like this. And then here, you maybe have this. All right. So if I was to compare the measurements, because you're effectively measuring the bullseye. So every time you're aiming for bullseye, then what I would say is that the person down here on the bottom left was neither precise nor accurate. Why do I say that? Well, they were aiming for the bullseye and they took three shots. If I take the average value of their position, it would be about here. That's far away from what they were aiming at. So their average measurement did not reproduce what they were trying to measure. So that's not a very well calibrated instrument. And then if I compare the position of each shot, each one is far away from the other. So the instrument is also not precise. Precise is a measure of how reproducible an instrument makes the same measurement repeatedly, right? So this would be low accuracy, low precision. Okay. We can then go up to the top left corner. If I compare that to the bottom left corner, the grouping is much tighter. All of the shots are much closer to each other, but they're all nowhere near the bullseye. So that would be precise. The instrument very reproducibly captures the same data when you attempt to capture the same data over and over, but it's just not accurate. So that's inaccurate. All right. So the average position is far away. So to determine if something's accurate, you determine what's the average measured value compared to the actual measured value. All right. We can now go down to bottom right. On bottom right, do the same game again. And we'd find that the average of the three measured positions is actually right on top of the bullseye. So that is accurate. But each shot is far away from the other, meaning it's imprecise. So you have an accurately calibrated instrument that is not very precise, and any given shot might be nowhere near the bullseye, but the average, if you throw enough shots, is the bullseye. So this is a calibrated instrument that just doesn't give good reproducibility shot to shot. Finally, top right. Three shots, all pretty much on the bullseye. Average value is the bullseye. This is both precise and accurate. The average value measures the bullseye, and every single shot is very close to the preceding shots. So that's basically the four conditions that can allow one to conceptually understand what is meant by precision and accuracy. All right, finally, we can discuss significant figures. Significant figures are needed because when you make real measurements in the real world, you only know something to the level that your instrumentation is capable of knowing it, which depends on how many measurements you take and how accurate and precise your equipment is. And so, what is meant by a significant figure is to tell the reader how much they can infer about how well you know something. And so, the way this works is if I can write the same number a few ways, let's say I know something, let's say something's actually 22.5. Well, depending on my equipment, I might say 20. That would imply that it's a little ambiguous, but that would imply that I either know it to one or two significant figures. I might say 23. That would imply that this is the significant figure. I know the threes place plus minus one. Or I might say 22.5. That means I know it's 22.4 to 0.6. Or I might say 22.55. That means I know it's 22.54 to 22.56, for example. Right? So that's the purpose of significant figures, is it allows the reader to know to what level of precision they can use the data. The important things for our purposes is how do significant figures work in the context of mathematical operations? So for that we can do addition or subtraction, or multiplication, and division. We'll start with the second. When multiplying or dividing two numbers that might each have a certain number of significant figures, the rule is, so let's say I have 22 times 54.3. So what I have to do here is I have to first say, how many significant figures does each of these have? This one has 1, 2. This one has 3. So the rule for multiplication or division is that my answer should be reported to the fewest number of significant digits shared between all of the things being multiplied or divided. In this case, it would be 2. So if we do this multiplication, we would see that 22 times 54.3 is equal to 1,194.6. But I can only keep two significant figures, so I should report the answer to this operation as 1,200, whatever the units are, where we round the significant figure based on what comes to the right of it. All right, we'll do another example just to also highlight how significant figures work. Let's say we had a number of 1.20. We're going to multiply it by 12. All right, so in that case, we have to do the same thing, and I highlight this example for a certain reason. Trailing zeros, like this, must be significant, meaning when we're to the right of the decimal point and the number furthest to the right is a 0, there's only one reason to include that 0. It's that it is significant. So this would have 3 sig figs. This has 2. So my answer should have, again, 2 sig figs. Yeah. And if I do 1.2 times 12, I'll get 14.4. And I should report that as 14 units. All right, now what happens when we add and subtract? All right, well, when we add and subtract, what we do is instead of keep up here, we keep fewest sig figs. Down here, we keep fewest decimal places. So what I do then, let's say I have two numbers. 3.5 plus, say, 450. Well, now what I would do is I would say, okay, this has 1 decimal place, and this has 0. So I'm going to report my answer to 0 decimal places. In which case my answer, well, the long form answer would be 453.5. Well, this one I'm not going to include because my significant figure will be in the ones place. So I would report that as 454. And finally, one last whole thing together. Let's say I had something that looks like this. This is all right, back to where we were. We're going to combine both rules in a certain operation. So let's say we had the numbers 12.1 times 3.2 plus 4.0 times 12. All right, so what we have to do is PEMDAS, right? Your order of operations, which says multiplication should come first, and we have two of those. These two numbers get multiplied, and these two numbers get multiplied. All right, we can do that. Let's see. 12.1 times 3.2 is 38.72. How many significant figures should we carry through that operation? Well, this one had 3, and this one had 2. So the 8 is the significant figure in our intermediate result. We're not going to round an intermediate result. We're just going to keep track of where the significant digit is. Then we can do 4.0 times 12 would be 48. And in this case, both numbers have 2 sig figs. So the 8 is the significant figure. All right, so now we're going to add these. And we're not going to round up front. So 48 plus 38.72 is 86.72. Where's the significant digit in each case? Well, this one's in the ones place. And so is this one. That means my result should be reported to the ones place, in which case I would report this as 87. All right, that's a pretty good review of how significant figures work, why you use them, and the key steps you have to use to get the math right.